In this video, we will discuss the sampling theorem. What is sampling? What are the different types of sampling? And we'll also look at the proof of sampling theorem and the effects of sampling. So first, let us start with what is the definition for sampling. If you look at the slide here, we are defining sampling as the process of converting a continuous time signal, which is denoted by x of t, into a discrete time signal that is denoted by x of n. So sampling is nothing but the process of converting a continuous time signal x of t into a discrete time signal x of n. How? By measuring the amplitudes of continuous time signal at integer multiples of sampling intervals. So we are going to measure the amplitudes of the continuous time signal x of t at integer multiples of sampling interval ts. So basically, if your continuous time signal is something like this, let us say if your continuous time signal is looking something like this, this is our time axis, right? How do we create a sampled signal from how do we create a discrete time signal from this continuous time signal? At 0, I will take my amplitude of the continuous time signal, right? Somewhere over here. Again, at 1, I will take the amplitude. At 2, I will take amplitude. At 3, I will take amplitude. At 4, I will take amplitude. Similarly, at -1, I will take the amplitude of the continuous time signal. At -2, I will take the amplitude. At -3, I will take the amplitude. -4, I will take the amplitude, right? At each discrete points, I'm going to take the amplitude. Discrete points, right? I'll take the amplitude, and the signal here, which is represented by the yellow color, is nothing but the discrete version of the continuous time signal, right? The signal in yellow color is not continuous. In between -2 and -1, there is no signal defined, yellow color, right? So this is nothing but the sample version of my continuous time signal. How did I obtain this discrete or sampled signal, discrete signal or the sampled signal? I am just measuring the amplitude of the continuous time signal at integer multiples, right? Integer multiples. So in general, I can write this integer multiples as multiples of ts, right? I will write this as multiples of ts. So what is ts? Ts is the sampling interval. Sampling interval. So how many samples per interval? So what is the distance between the two continuous samples? The distance between the two continuous samples is nothing but the sampling interval Ts. So this is how we will sample a given signal. So sampling is nothing but a process of converting a given continuous time signal x of t into a discrete time signal x of n by measuring the amplitudes of the continuous time signal x of t at integer multiples of sampling interval. This sampling interval is user defined. The user defines this sampling interval. Here I have taken my sampling interval to be this much, right? So between the two successive samples, the ts is the distance between the two successive samples. So suppose let me take a sine wave, or yeah, I'll take a sine wave. I will only consider two samples per cycle. Now this is one cycle, right? Starting from here till this point, right? Till this point. This is one cycle. If I consider only two samples per cycle, how will my sine wave look? I'll consider one sample here I'll consider one sample here, and I'll consider another sample here, right? I'll consider another sample here. Now if I consider four samples, let me draw with a different color. I'll consider one here and one here, the third one here, and the fourth one here. If I take 5 samples, I'll consider one here, right? So based on the number of samples, my TS varies, right? If I consider 2 samples, the time between 2 successive samples is, let me say, it is definitely a bigger value than the time between successive samples when I consider more samples. More number of samples, TS will become smaller. Lesser number of samples, TS is bigger. Now, if we look at the main application of sampling, what is the main application of sampling? So most of the signals are analog in nature, right? Most of the signals are analog in nature. But to store an analog signal, we need a lot of space, right? For every instant of time, there are infinite instances of time. So for every instance of time, there is some value for the analog signal. So if you want to store infinite values of analog values in the computer or in any storage disk, it occupies a lot of space. In order to reduce that storage space, we will sample. We will do sampling. So sampling is done. The main advantage of performing sampling is to reduce the storage space, to make use of the digital technology. The first one is reducing storage, right? Reducing storage. And the next advantage is we are making use of we are using sampling to take advantage of digital technology. What is the advantage of digital technology? It is inexpensive, right? It is definitely inexpensive than analog. And what is the next advantage? It is portable or definitely lightweight, right? Lightweight. And one more advantage will be you can program your digital, you can program, right? You can program your digital technology. However you want your digital technology to work, you can program it. It is very simple. You don't have to change the hardware. You just have to change the program. And finally, it is easily reproducible. Easily reproducible, right? You can reproduce. Once you create a digital system, it is very easy to reproduce. If you create an analog system to reproduce the analog system exactly, it is not possible. There will be slight variations, but in terms of digital technology, it is very easy to reproduce your system. So these are advantages of sampling. What is the need for performing sampling, right? Then this one of the applications, ADC, right? ADC, analog to digital converter, is one of the main applications of sampling. Sampling is the base for ADC, analog to digital conversion. So we have a signal which is continuous in time, and continuous in amplitude, right? The signal exists for any value of time here. Any value of time the signal exists, and it can take any amplitude. The amplitude also, it can take any value. That is, it is also continuous in y-axis. It is continuous in x-axis and it is continuous in y-axis. Right? This is the analog signal. So in order to convert this analog signal into a digital signal, in order to convert the analog signal into a digital signal here, the first step is sampling. We will sample the analog signal. We will sample the analog signal. How do we sample the analog signal? By measuring the amplitude, right? As we have shown in this picture, we will sample. If we sample the x-axis or the time axis, right? That means we are discretizing the time axis. That is called sampling in time axis, right? If we sample the time axis, what will the result be? The result will be a discrete signal, right? What is sampling? It converts continuous time signal into a discrete time signal. So if you first sample in the time axis, the result will be a discrete signal. We will obtain a discrete signal from the given analog signal. This is sampling in one axis. This is where we obtain the discrete signal. Remember, this is discrete signal, not digital signal. Digital signal is different from discrete signal. If you sample in one axis, that is the time axis, the result will be a discrete signal. After that, if you also sample in the y-axis, that is the amplitude axis, which is called quantization. We call sampling the amplitude axis as quantization only if you perform sampling in both y-axis as well as x-axis, right? The amplitude axis as well as time axis. The result will be a digital signal. The result is going to be a digital signal. This digital signals you will learn later in other subjects. In this subject, we are only concerned about discrete signals, converting an analog signal into a discrete signal. The quantization along the y-axis, these and all we will be seeing in subjects like analog communications and digital communications. So just remember for now, to convert an analog signal into a digital signal, first the analog signal is converted into a discrete signal, and then the discrete signal is converted to a digital signal. This is called this conversion. The first conversion from analog to discrete is done by sampling. We call this as sampling. And the second step of discrete to digital conversion is called quantization, right? Let me write it clearly. It is called quantization. Quantization, right? So this is about sampling. So let us see what are the different types of sampling. There are three different types of sampling. The first one is instantaneous sampling or ideal sampling. The second is the natural sampling, and the third will be a flat top sampling. Instantaneous sampling, natural sampling, and flat top sampling. Let us look at what is instantaneous sampling. Instantaneous, that means at that instant, right? The signal is sampled with the help of impulse train. To perform instantaneous sampling, we use a impulse train. How? We will multiply the given signal. Here the dotted signal, look at this figure. The dotted line is nothing but the analog signal, our original signal. Let us consider it as f of t, right? And I have a impulse train, and I have a impulse train. So I have one impulse here and another impulse at this point, this point, this point, and so on. I have an impulse train, right? This is my impulse train. So if I multiply my dotted signal, that is the analog signal, with the impulse train, how do I define my impulse train? Delta of Ts, delta Ts of t. What is Ts? Ts is the period. Ts is the time period, right? Ts is the time period. So if I multiply my analog signal with the impulse train, what is it? I will get my sampled signal. So at 0, I have some value for the analog signal. It is some negative value for the analog signal. And I'm just multiplying it with my impulse train. So my amplitude of the impulse train changes to whatever is the amplitude at that point at 0 for analog signal. So at Ts, this is Ts, right? So Ts, I have an amplitude for the analog signal, which is, let us say, some 2 volts or 2. Now I am going to multiply that with the impulse at Ts, right? So I will have an impulse here with an amplitude of 2. Then at 2 Ts, let me say it is 4. At 4 Ts, it is 4.5, right? And so on. Here again there is a negative value. So whatever I have an impulse here, I'm just multiplying it with the negative value. So my resultant impulse will be negative, right? So this is how we will perform instantaneous sampling. The signal is sampled with the help of an impulse train, and the sampled signal consists of train of impulses of differing amplitudes. The sampled signal, which is shown here in the pink color, is nothing but it is a train of impulses of differing amplitudes. Train of impulses with a differing amplitude. Then the second type of sampling method is natural sampling. So in practice, okay, let us see, this is an impulse. It has a width of 0. The width of the impulse here is 0. In practice, it is not possible to create such a signal, right? I cannot create a signal with width 0. I can't switch on a waveform generator to create a impulse function and instantaneously it has to become 0 again, right? I can't switch on and switch off my waveform generator at the same time, right? This is not possible in practice. Practically it is not possible. So practically my impulse will look something like this. It will look something like this with a very small width, not 0 width but very small width. So we will consider this as an approximation of impulse, right? In practice we'll consider this as an approximation of impulse. So if I multiply f of t with a train of finite duration pulses, so what is my train of finite duration pulses? It looks something like this, my train of finite duration pulses, right? Finite duration pulses. Instead of impulse, I have a train of finite duration pulses. So these are my train of finite duration pulses. If I multiply my f of t or the analog signal with the train of finite duration pulses, how will it look? It will look like this, right? This is the starting point of my pulse here, and it has a constant amplitude here. When the constant amplitude is multiplied with my analog signal, I'll get my analog signal. Let me consider the amplitude here as 1. So 1 multiplied with any value is the same value, right? So this is how my sampling looks like for the natural sampling. This is how natural sampling is done. In practice, this is how it is done in most cases, right? So what happens in this type of sampling, each sampled each sample has a varying amplitude. This is one sample, this is another sample, this is another sample, right? Within each sample, the amplitude of the sampled signal is varying. It is varying according to the analog signal. So this is the second type of sampling, which is natural sampling. Next we have a flat top sampling. Flat top sampling. Flat top sampling is very similar to natural sampling, except that instead of having a varying amplitude within the sample, instead of having a varying amplitude, I have a constant amplitude. So what I am doing here, I am taking the amplitude of the analog signal at the starting edge of my train of pulses. So if this is my train of pulse, for the first pulse, I'm going to multiply it with the analog signal. My analog signal is something like this, right? My analog signal is something like this. So what I'm going to do, I'm going to multiply my first starting edge with the analog value here. So I will take that value, I'll obtain a value, and I'm going to keep that value as constant for the rest of my impulse train, or rest of my pulse train, right? I'm going to hold that value. I'm going to sample, I'm going to take this sample, and I'm going to hold it till the end of my train. So at this point, I'm going to sample the analog signal and I'm going to hold it. I'm going to sample the analog signal and I'm going to hold it, right? The signal is sampled at a particular instant and the sample value is held for the rest of the duration of the pulse. This is the third type of sampling. So the three types of samplings are instantaneous sampling. Whatever is there at that particular instant for the analog signal, we will take that value. And natural sampling. We will consider train of pulses instead of train of impulses, and the value of the sampled signal keeps varying according to the analog signal within the pulse duration. Now for the flat top sampling, I will sample at one instant I will sample at a particular instant of the analog signal and I will hold that value for the rest of my pulse train, rest of the pulse, duration of the pulse. So these are the three types of sampling.